In this activity, we are looking at the idea of a sampling distribution. So first of all, we're going to start with a population. A population is a set of all individuals, all right? So we're going to start with a very tiny population to keep the scenario simpler. We have only 4 people who took a midterm, and we're going to try and figure out their midterm exam, all right? I always hate it when that little thing shows up there. It went away. All right, so their midterm exam scores are 60, a 70, an 80, and a 90. And I went ahead and I created this dot plot right here. And it has the 60, the 70, the 80, and the 90. And I used the one quantitative variable and Staplet. And it gave me the mean and the standard deviation and the size. So you can take a sample of any 2 scores and find the mean of your sample. So I asked the students in class, just pick any 2 you like. And then we went through the class and I asked each table to give me one of their samples until we came up with all the possible samples. So we were able to do 60 and 70, 60 and 80, 60 and 90, 70 and 80, 70 and 90, 80 and 90. Now, this is the entire population, all right? So this is the entire population right here of samples. So this is what a sampling distribution is when you look at all the possible samples. And I made a little dot plot of all the possible samples right here. There's your 65, your 70. We have 2 75s, an 80, and an 85. And we looked at the mean of that. And, oh, I forgot to put a little bar on there. There's supposed to be a little X bar there. So this is the mean of the averages. I know that sounds weird. The average of the averages of the samples. So it's means for all samples of size 2. And there are 6 of them. So that's kind of interesting. We went from a population of individuals of 4 to having 6 different samples from the 4. And there's a way to calculate that if you remember the counting methods that we learned in the fall. I have 4 to choose from. I can pick 2, and the math for that turns into 6. Now, so the amazing thing is not, maybe it's sort of expected that the average of your samples should be the same as the average of the whole population. So you can see the difference in the symbols here. You have just mu, like mu alpha theta, and then you have mu of x bar, which means it's the mean of the averages. This is the mean of everybody. This is the mean of the averages. Okay, you should be able to tell me what each dot represents. So for example, this represents one sample where the average is 70. This dot plot is called a sampling distribution. It shows the means calculated from all of the possible samples of size 2 from the population. So on average, all samples put together average 75. Individual samples aren't necessarily 75. So it doesn't mean that if you take a sample, you will get 75. But on average, the samples will give you the same mean, okay? Also, the cool thing is the less variability in samples than populations of individuals. What do we mean by that? Well, there are a couple things you could look at. You could just look at the standard deviation, which is how much things vary. And here it's 7, and here it's 12.9. Also, if you look at the minimum value here, it's 60, and the high value there is 90. The minimum value here is 65, and the high value is 85. So you can already see that it's tightening up the numbers a little bit. So less variability, and that's the whole point of sampling, is we want to get less variability, get closer to the true average. Okay. In reality, there were many students who took the midterm, and here's the set of data. So it's going to be too difficult to create every possible sample, so we're going to simulate how to do that. Now, I went ahead and shared this Staplet. I guess if you want to do it, can I click on it right now? Let's see. And yeah, there it is. So I generated this Staplet, and if you generate 2 sets, we're trying to create 2 samples with 5 students in each one. And my lowest student number is 1. my highest student number is 146. So it's important to notice that these are the student numbers and the scores are the numbers in bold. All right, these are the scores right here, okay? So we're trying to average the scores, not the student numbers, but the scores, all right? So anyways, we're gonna go ahead and create two samples. So I hit get sets, which you can't see right here. Let me make it so you can. Get sets. And then it says, oh, you're going to get student 1, student 6, student 8, student 13. Oh, why is it so low? Because I forgot to put 146 in there. And then because I'm going from 1 to 146, get sets. Ah, that looks more like it. I mean, not that I couldn't have 1 and 6, but there was nothing very high, so I could tell there was a problem. So 43 and 65. So I would go back and I say, oh, student 43, what did you get? You got a 65. So I would put a 65 here. So I'll just show you. So I'd have 43, and that would be student 6, and that score would be 65. And I know my other score, my other random number was a 65, so which is kind of weird. Hope that's not confusing. That's not a score, that's a student. Student 65 scored a 63. All right, so scores aren't looking too great so far from what I pulled, right? So you basically just get your student numbers, look up their score numbers, and put your average test score. You add up this bottom row, and then divide by 5, all right, because there are 5 scores. So everyone did that, and they wrote their mean on a sticker, so for both their samples, and they put them on a poster, and so this is what one of my classes got. So, in fact, they were actually one of the furthest away, which is kind of funny. Population mean, well, you know this now, but they didn't know it right away. So this is their estimates of what the average for the class was based on their samples. And the average for their samples was 74.75. And the average for the true population mean was 75.98. So you can see that they're both very close to each other, which is great. All right, now you're going, but they're not exactly the same. Well, I didn't take the entire sampling distribution. We only did 44 samples, and I'll address that later. What does each dot represent? Basically the same idea. It represents one sample average of 5 midterm scores. And don't worry about the pink yet. We'll come back to that. So we know the true mean is 75.98 here, right? And actually, let me erase it and put it in a different color so you don't mix it up with the pink. So we know the true mean is actually 75.98, and I actually have the set of data. I put it in the Statlet, and here's the data. So are we going to say this is biased? No, it's not biased because the means for the population in our simulation are very close to each other. Now, if I had done every possible sample, then the means should match. Here's why I'm not doing every possible sample. There are 146 students to choose from, and I'm taking 5. That's over 515 million different possible samples. Not doing it at all. Okay, then we took a random sample of 5 midterm scores at Rockford High School and got a mean of 68. Is this convincing evidence that Rockford students did worse than students at our school? Well, in our particular simulation, so this is why I have the pink, 5 out of 44 times, so there's 1, 2, 3. So let's look at the question again. I went a little fast there. We took a random sample of 5 midterm scores at another school. And we're trying to say, are we better than them? Or are their scores lower than our scores? Well, we look at our simulated sampling distribution. Notice that does say simulated there, right? And 5 of the students in this period, or 5 of the samples in this period, because each student took 2 samples, are 68 or lower. Actually, they're lower than 68. It's 65, 66. That looks like 62 and 60s. So 5 out of 144 times, that's about 11% of the time that I can get an average that low. So it's possible that Rockford has the same average we do, and they just we happen to get one of those low samples. And that can happen 11% of the time. So we're not that surprised. We're not convinced they did worse. Now, I added some extra practice because of what we were doing on the check for understanding, which I'll record here in just a sec. What is the probability a student scored lower than 72 if the population is normally distributed with a mean of 75.98 and a standard deviation of 15.5? So first of all, let's take a look at the original population, which I happen, if you look at the very beginning of your activity, that right there on the corner, that's the original population, okay? And it's not normally distributed, it's actually skewed, all right? So if I were to try to guess individuals on this, I would have a problem because this is a skewed distribution, and if I try to use a normal distribution, it doesn't really work so well for skewed distributions. So I made a slight change to my question, and I said, imagine that it was normally distributed. Okay, pretend it's normally distributed. So that allows me to do the normal distribution applet. And so we want, the model is 75.98 with a mean of 15.5. So www.stapplet, normal distributions, 75.98, 15.5. So that's the distribution of scores if it were normally distributed. All right. And we want to know that what is the probability a student scored lower than 72? So I would just go ahead, go lower than 72 to the left of the value, 72. Calculate, show the labels. And you can see that the area is about 0.3987. So about 40% of the time, students would score 72 or lower if it was normally distributed with the mean of 75.98 and a standard deviation of 15.5. So I copied that answer down in here. There it is, 0.3987. So what is the probability that a sample of 49 students average 72 or lower? So I actually have to go and I still get to use the normal distribution. But what happens is it tightens up. Remember what happened here when we went from the population to here. And in fact, if you look at your notes, right in here, unfortunately, what happened is you would see that, yes, these actually got much tighter. And unfortunately, I don't have a little video. The variance decreases and increases. So in other words, your variability goes down as your sample size goes up, all right? So our variability goes down. And then the other effect that happens is even if with this skewed distribution, I could still use a normal distribution for the sample because I met something called the central limit theorem. Central limit theorem says when n is at least 30, the shape of the population doesn't matter. The means are normal shaped. If the population is normal, any sample size works. So this is what that's why I said here, for individuals, the population shape matters. This is a question about an individual. So I had to say it was normally distributed so I could use a normal distribution. This is for a sample, and it's 49 students. So it doesn't matter if it's skewed or not. This would actually work for the original data that's skewed. But I do need to go ahead and adjust and calculate my new standard deviation. So I take my old standard deviation, which is 15.5 here, and I put it in there, and then I divide by the square root of the sample size, 49, and I get 2.21. So now I have a new model, and I go back to my stapplet, and instead of 15.5, I put 2.21. Plot the distribution, ask the same question, and now you can see it's much tighter. So it feels like, whoa, what happened? The problem is this doesn't scale skinnier, so you don't see the effects so much. But if you look right here, the values there, actually there is a stapplet I can show you. Hold on. To show the same effect. there is simulating sampling distributions. So I could actually have, let's say it's skewed, all right, and I'm doing samples to size 49. So I'm going to select a sample, and it makes sense that the data is on the lower end, but I can add, select, so that I'm going to do the sampling distribution of the mean, and I'm going to add, let's say add 100 samples, okay? Look how approximately normal that looks, right? So it doesn't look skewed at all. And if my sampling size was smaller, we'll do 30, all right? And then I add 100 samples. It's getting better. It's getting better. If I do sample size of 100, right, and select samples, it should get really very close to normal. So now if I was doing sample sizes of, say, 5, there's still a little skew. You see the skew there? So 30 is the magic number in the guideline that we say for pulling up that we can use a normal distribution. This is 49. 49, we can totally use a normal distribution. So I have the normal model, and I calculate it, and I got a much smaller value of 0.0359, or 3.59%. At least I think that's what I got. Let me go see. Yep, 0.0359. Okay, so the shape is normal because the original is normal. If the original is skewed, you need samples greater than or equal to 30.